Okay, thanks a lot, Naomi and Mats. Yeah, I think that you can open your screen as well. My name is Natalia Konchakova. I am the coordinator of VIPCOAT project, and I will give now the presentation about the meeting. But first of all, I would like to thank Mats, Naomi, Chan, and this young researcher, corrosion researcher group for give us the floor to present the final results of the project and to disseminate this really great collaboration activity of 12 partners. But more information I will give in 2 minutes. Mats, maybe some words from your side.
Yeah, so I would like to thank the Young YEFC for giving us the opportunity to present, I think, a very extensive work between a lot of European partners to successfully work in two fields, an open innovation platform, but also on a practical level for corrosion researchers and work on a platform that we can all use, and that we will try to show you that after this, that it doesn't stop here with the presentation, but afterwards you can all go to our website and try to work with it, give feedback, and try to collaborate with it, because it's important that we keep collaborating on this topic or topics, and that we reach even a broader audience and a broader outreach or scientific output even. So I will leave the introduction to Natalia, but I will be back for giving a part of the scientific contribution.
Thank you. I will start my presentation, and I hope that you can see my screen. Is it the case? Yeah, Mats?
Yes.
Okay, yes. Thank you very much. Today we will show you the results of VIPCOAT project. We will speak about open innovation platform as the tool to co-creation of sustainable protective coatings based on predictive modeling and focused collaboration. As Mats already say, it is not the finish of our collaboration. It is the start of the work at the platform, and we will be happy to motivate you to use this tool. You can see now the names of all 12 partners, and now I will say some words about the project and the webinar today. Stop. What does not work? One moment. Yes. Some words about the webinar. We are very happy to see now here young researcher and maybe experienced researcher as well who are working on corrosion protection, and we will give you some novel technique and research results which we investigated and created in the frame of the project. The presentations will be available at the webpage of the project, and of course from Jan research community for corrosion protection as well. If you have any questions and suggestions to improve the open innovation platform, your feedback is very, very welcome. And we have the special form at the platform. Here is the link. Please go here and express your opinion. About the event today, we will start with the short introduction of the project. Yeah, I will do it. After that, Marko Horvat from Wikki Ltd, it is a company in UK, will give the overview of the platform itself. After that, we will show you 4 applications focused on the modeling, materials modeling of different aspects of development of the corrosion protection. And our partners from different companies and different research institutions will give you this overview. We will have a small break after presentation of applications, and after the break, Marko and Lisa Sahlmann from Helmholtz-Zentrum Hereon will give you some examples how to use the platform, how to create your workflow for coating performance, and it would be on the end session for questions and open discussion. So, welcome to VIPCOAT.
Welcome to VIPCOAT.
we created an open innovation platform to connect science and industry. The platform serves as a database, scientific infrastructure, and simulation tool at the same time. Machine learning and physics-based modeling are combined to optimize industry-relevant active protective coating development processes. VIPCOAT is designed to support the industry in the development of customized innovative corrosion protection technologies. You can use the platform to share your ideas, find relevant partnerships, and accelerate your innovation via embedded tools for coating characterization. Start designing the future of sustainable and environmentally friendly protective coatings. Join now.
Yes, we developed our visual open innovation platform for active protective coatings guided by modeling and optimization. It is a 4 years project which started in May 2021 and which will be finished in 1 month. Yeah, we worked together, 12 partners who represented the whole Europe, and who are working very intensive on new corrosion protective active protective coatings, and to provide these excellent tools to cooperation and create these coatings together. It is open innovation platform. But the platform was focused to bring this innovation together based on quadruple helix innovation model. And the core of the call, it was creation of this platform. We built a platform to join industry, governmental body, university research institutes, and society to solve the problem on the forward protective coatings. And in this slide, you can see the schema of this model to bring all these 4 important pillars to work together in collaborative environment, digital environment. The potential roles of actors, you can see here, industry bring for innovation, market needs, and innovation development. RTO can support the industry to solve all questions and to give the decision support system. The government, or here it is as administration, will give the regulations. For example, currently we are working on the digital product passports for materials and for products to follow, to implement the Green Deal conditions. And society, it is the customer, of course, and it is the people for whom we deliver all our work. VIPCOAT innovation process and innovation accelerations schema, you can see here at this slide, where collaborative industrial innovation along of productive chain are depicted. We have in the consortium 3 companies. It is the first company who produced the pigments and nanoparticles, active nanoparticles for paint system. It is Smolmatec. Second company, it is AkzoNobel, who integrate these extenders in the coatings system, and Airbus as the large industry and large customer of the end product use this new coating system and check it in the environment condition, in the industrial conditions, and give this flow from business to business to business to evaluate this platform and evaluate the coatings as well. This collaborative environment implemented in digital resource is the open innovation platform. We are providing this collaborative decision-making system, and we are working on the application of serious gaming theory for the quadruple helix innovation model as well. Now I will speak about the scientific challenges and scientific core of the project. It is the modeling-supported design of new protective coatings. Here it is business to RTO schema when we can consider requirements from industry and finding the new solutions by research organization. I think that many of you already heard and seen this picture from, for example, from Euro conferences and congresses, where we organized a focusing session and many partners from VIPCOAT project already presented the results. And you know, of course, as the EU specialist in corrosion protection, this schema for active protection coating. For VIPCOAT project, we developed 4 applications. First, it is corrosion additives and selection of the best inhibitors for coatings. And we are designed and developed this machine learning technique to provide all this selection. The next application, here the focused industrial user is Smolmatec, and RTO or universities, it is TU Delft who provides the data for this application, and Hereon who creates the model. The second application, it is inhibitor delivery and creation and analysis of microstructure of coatings based on the geometry of pigments and real data from DAISY experiments. And here modeling partner is Fraunhofer ITVM, and Hereon supported to conduct the experiments. Smolmatec involved in this development as well, and AkzoNobel as industrial partner. The behavior of coatings in their static and dynamic conditions are 2 additional applications as the material degradation of the coatings in the coating defects and degradation under dynamic conditions. And here the focused modeling experts are VUB and Elsica, and TU Delft and Hereon supported this modeling efforts by providing experimental data. And Airbus and AkzoNobel are working as well as industrial partner and contributor from the experiment part and testing of the new coating systems. All this information and models are integrated in the platform. And VIPCOAT OEP and the innovation process you can see here. I would like to thank the group of partners who are working to implement this complex software system. It is first of all Wikki, who is leading of this activity and who is the main developer of the platform, but the contribution from LIST, SINTEF, Fraunhofer and NTNU supported and successfully give the input to implement this system. You can see the link of the platform, and Marko Horvat will give you more information how to work this system. I would like only to show you that you need to be logged into the system, and after the login you can see all 4 applications integrated in the platform and availability more other tools which will help you to go to digitalization of your materials and to work efficiently with this digital environment. Good. Here you can see the link of the platform. You can see some links for YouTube channel where we already have. And I would like to go now to give the floor to Marko Horvat to present the platform and to give you more information about this tool. Thanks a lot for your attention.
Yes, thank you very much, Natalia, for the kind introduction. Hello, everybody. My name is Marko, joining you from London. And in the next 15-20 minutes, I will try to go through a very brief overview of what VIPCOAT platform looks like and what can you find there and things like that. Let me just share my screen. No, not like this, the entire screen. And please let me know if you can see it. Yes, okay, great. Okay, as Natalia already told you, if you navigate to VIPCOAT-oip.com, you will be redirected to this landing page where at the first glance you will have limited access because you're still not logged in. So let me just go through what you can see here currently. In the top left corner, you have two buttons. The first one is a drop-down menu that gives you access to a general information about the project, so you will be able to find out what is our aim, what the project is about, who are the partners, where the funding is coming from, what's the grant agreement number of the project, and so on and so forth. Another thing that you will be able to access is the feedback. So you are either able to go to the link that Natalia gave you in her presentation about providing us the feedback, or you can just come to the platform, click on give the feedback, and this will present to you a form that is anonymous if you would like to stay anonymous, so you don't have to provide any personal information to. But if you would like for us to give you the answer to your feedback, if you have any questions, you are able to just drop your email address over here and we will make sure to answer any questions that you have. And this form is just guiding you over questions about the usability of the platform, how useful the platform is, and similar questions. So you can just scroll through it at the end of the presentations today and just tell us what you think about the platform. One very useful feature is if you just click on the logo at the top left corner of the platform, it will navigate you to the homepage of the platform. So if you ever get lost in the content of the platform, you can always just click on that button and it will bring you to the homepage. Another thing, if you get lost in the usability of the platform, you have this booklet icon. You can click on it and it will open the documentation page where you can go through more details and more theoretical aspects, but also the usability aspects of different parts of the platform, such as you will have information about use cases. So for example, if you click on use case 1, you will be redirected to a page which describes this use case, what are the KPIs, how it works, what are the connections, which chemical database are we using, some publications in that front, and also how to use the platform and what are the expected outcomes. If you are looking for something more specific, but you don't know which exact section of the documentation this would be found in, you are always able to just search for it. For example, Natalia mentioned quadruple helix. So if I just type in this search bar quadruple helix, it will present me with the sections where the quadruple helix can be found. And then clicking on the section will bring you to, for example, collaborative environment where quadruple helix and the idea of quadruple helix and how it was implemented in the platform will be shown to you. Okay, so going back to the platform, now probably the most important part of it. So how do you actually log in and how do you get access to all the more interesting topics and more interesting content of the platform? So in the top right corner, you have the login button. You can click on it and this will redirect you to our login page. If you already have your username and password, or if you have our account at our platform, you will be able to just populate this form, and you will be logged into the platform. But if you are visiting us for the first time, there are two options for you that how you can log into the platform. First, we are allowing third-party identity providers such as GitHub and Google, and you are able to use your Google account or your GitHub account to log into our platform. If you would like to have a particular VIPCOAT account, you can click on the register button at the bottom, and this will open the registration form where you are able to provide your personal information, and also you can choose your password and username. And after clicking on the register, the platform will just send you one final confirmation email to just check if the email address is actually associated with your email address, and you will be able to just click on the link provided in the email saying, I confirm that this is my email address. After that, you will be able to use this account to log into the platform. Okay, going back to login. So as I said, you just have to populate your username or email and password, and clicking on sign in will redirect you back to the platform, but now with complete access to all the VIPCOAT functionalities. Okay, let's take a look what is now new. You can see these two buttons that Natalia already introduced in her slides, but now you can see them in the platform itself. The first one, this factory icon over here, is again a drop-down menu where you can just go and scroll through through different use cases that the VIPCOAT considers important for the corrosion protection. And going through app 1, 2, 3, 4, you will be able to just navigate to the landing pages of these use cases where the use case is described in more details, and yes, you will be able to start using the use case over here. The same goes for all the other use cases in the drop-down menu. The last icon on the left-hand side of the navigation bar is the toolbox, where you are able to go and take a look at the different tools that VIPCOAT is providing as essential tools that are used in in the execution of your collaboration projects, let's say it like that. The first one is BDSS, so this is a business decision and support system where you are able to just go and quickly glance through the data sets that you are currently working on, and this tool should in theory allow you to make better business decision when you are working on your data. The second ones are the public data catalog. Here is the public data catalog is a collection of data documentation that can be further used in the simulation tools. So if I just click on show everything, you will be able to find the documentation of, for example, results from the experiments, such as the one over here. Clicking on it will redirect me to a resource page where I am able to just glance through the metadata that are associated to this particular experimental evaluation of inhibition efficiency. So I will be able to see what particular files are associated to it, how big are the files, where can I download the file, when it was created, and so on. Additionally, there is this pipeline aspect over here. Pipeline gives more information of how to use the data. So for example, if this is a table-like structure in this particular format, which is binary over here, the pipeline will give me information of what will I be able to find inside of it, so that the parser knows how to parse this particular data structure, and also the mapping configuration, where we are pointing with the, for example, data points that we can find in this particular file into some common ontology, where the semantic meaning is given to the data points inside of this file. Okay, but this is going a bit too technical. You just have to remember the data catalog is the place where you can document your data, and where you can, which you can use to share the data with your simulation tools, but also with the members of your partnerships when you are working on the project together. The next one is the worker catalog and workflow catalogs, but this I will go through in the second part of the platform demonstration, because this goes into more details and more complex functionalities of the platform. Let's in this first session go through something that is not so technical. Okay, so we are now finished with the left-hand side of the navigation bar. On the right-hand side, probably the part where you will spend the most time at the beginning, when you are just trying to define what is, who are you, and how would you like to collaborate with others, is your user page. So clicking on that icon in top right corner that now replaces the login button, you will be able to navigate to your user page. And user page is just a collection of your interactions with the platform. So first, what are some of your personal information, so the first name, last name, email, but also some other information that you would like to give, for example, your LinkedIn pages, GitHub pages, your CV, and so on. The platform here also collects what are you proficient at. So for example, if you are good at programming, just drop some programming languages over here so that everybody else knows that you are proficient in programming. If you come from other parts of industry, you can also drop these skills there as well. The user page also tracks who are you currently collaborating with. So it will give you just a list of teams that you are currently a member of. And the last part over here at the bottom is just your personal collection of the files that you are currently working on. For example, if I click over here, it will redirect me to post-processing of some results of this use case app 1. But you can add different files there as well, and you can also delete them if you don't want to have them there anymore. Okay, but how do you actually update any of the information over here? You have the button in the top right hand corner of this first card over here, where you can go into the edit mode of your user profile, and here you will be able to add new skills. For example, if I would like to add something else, I don't know, programming, I can just start typing the skill I would like to add, and then just search the database of skills that we are using, and then you are able to just click on add. If, for example, you are keen on working at with machine learning models, you can just add this skill to your profile. Once you are ready with the changes of the profile, you can just update or cancel the updates. Let's cancel it this particular case. And what else is there important in your user profile? So something similar as the public data catalog that I showed you previously, where the public resources are documented. There is also a user data catalog for something more specific to your work that should not be shared with everybody else. So there is the user data catalog. It's pretty much the same idea. The implementation is the same, and the way of using it is the same. But here you will be able to find something that is more related to your work, something that is more sensitive that you don't want to share with publicly, or something that is in the testing mode and you don't want to pollute the public data catalog. For example, I have here some simulation results. Let's just, I don't know, click on one over here. And I will be able to now, in the same fashion, just scroll through my simulation results over here that are documented in the same way as the experimental results that I've shown you before. We have recognized some data formats that are useful for a very quick introduction to the data that is stored over here. For example, some images where you are able to click on the image, and this opens automatically on the platform without you having to download anything, an animation from this simulation, and it shows you how your particular concentration of, in this case, the hydrogen cation is diffusing in the electrolyte of this system. But more about that in the App3 demonstration later. And there is also a similar functionality for tables. For example, if I'm interested in average quantities in the simulation results over here, I can click on preview table, and this will then give me access to this table, to the data in the table, where I'm able to just quickly scroll through the data and see if everything is okay, or what the results look like. For example, if I am interested in the same quantity, the H plus over time, I'm able to do that, and then I will be able to see what is the concentration of this chemical species inside of my system. If you are happy with this, you can always save it as an image. I will not do that, but just clicking on it, it will just download the image of this graph to your download folder, and that's it. You're also able to change the scales of the axis. For example, if you would like to take a look at this in the logarithmic view, you're able to do that as well. And then to exit this, you always have at the bottom this close button. Just clicking on it will bring you back to the data catalog resource over here. Okay, and finally, just before I finish this session, I would like to just mention these two additional buttons over here. So this bell icon is the place where you are able to take a look at your notifications. So whenever platform does something that requires your attention, the platform will send you a notification. For example, if the post-processing is ready of the simulations, it will tell you, oh, it is ready, go into your data catalog and take a look at what is happening over there. Or if somebody wants to deploy a workflow, okay, this is the admin functionality, but if somebody would like to invite you to their partnership, or if somebody joined your partnership, you will get a notification over here. And finally, just next to this button, just the extension of these collaboration requests, you will be able here to accept or decline any collaboration request that's currently pending for your attention. In the second part of the demonstration, later I will go through this collaboration process that we implemented in the platform, and we'll show you everything that is important over there. And with this, I would like to conclude this session. Thank you very much.
Thanks a lot, Marko. Yes, it is complex and very big system, software system, and part of the system is the applications. We are starting now to demonstrate applications, and first of all, it is inhibitor selection in efficient inhibitor prediction and selection, and Lisa Sahlmann from Helmholtz-Zentrum Hereon will present this work. Lisa, floor is yours. Please do it.
Thank you, Natalia. So let's share my presentation. Okay, I hope you can see it now, and I hope you hear me well. So my name is Lisa, and I'm a PhD student at the Helmholtz-Zentrum Hereon. And in the VIPCOAT project, I was working on the corrosion inhibitor selection workflow. I want to start off with a little thought experiment. Imagine that you want to find a suitable organic corrosion inhibitor because you are designing a new coating. You can run 6 experiments in parallel, and they take 24 hours. Then when we assume that the chemical abstract service database contains 10 to the power of 8 organic chemicals, we would need 68,000 years to test them. And if we even assume that there are 10 to the power of 63 synthesizable compounds, for comparison, the observable universe has 10 to the power of 21 stars, then we would need 10 to the power of 59 years to test all the molecules. And since we wanted to finish VIPCOAT a little bit earlier, we asked ourselves how to shortlist promising inhibitors for prototyping and testing. And this is the point where data-driven models come into play. So we wanted to develop a quantitative structure property relationship model. And with that, our aim was to identify the quantitative relationship between the properties of the molecules, and properties means, in our case, that they are suited for corrosion protection of our metal, and the structure of the molecule. And there are 3 prerequisites for this QSPR model. The first one would be sufficient and sound training data, including a target property. Sufficient training data in our case means we need enough molecules tested in the lab for their corrosion inhibition properties. Then second, we need input features for the model that are relevant for the target of the machine learning model. Input features means how we can encode the structure of the molecules, put them into the machine learning model. And the third point would be a suitable model framework. And now I want to go a little bit more into detail for all of the 3 points. So I talked about the target of the machine learning model. In our case, we were using the aluminum alloy 2024 T3, and the people at TU Delft conducted linear polarization resistance measurements. Therefore, the samples have been sanded and polished, and afterwards the samples were exposed to water solutions containing 0.1 molar of sodium chloride and the respective small organic molecule that we wanted to test. Then the LPR measurements have been conducted every 10 minutes for the first 24 hours, and the pH was measured before and after the experiment. As I already mentioned, we also needed to somehow encode the structure of the molecules. And this we did using so-called molecular descriptors. Molecular descriptors can be anything that you can put into numbers about the structure of the molecule. So here's some examples. It could be the functional groups in the molecules, or Euclidean or topological distances in the molecule. It can be density functional theory, and so on. So we can get a lot of different molecular descriptors. This is our overall workflow. So as I already mentioned, we start off with having the database. Then from the structure of the molecule, we get molecular descriptors. And we can get a really large number of descriptors here. That's why we needed to reduce this number to get a good machine learning model. If you just put all the descriptors in there, we would probably end up with a really bad model because not all the inputs are suited for the goal. So we went for a group feature selection approach called recursive feature elimination. And here, it's basically training a model, in our case, a random forest. And then there's an internal ranking of the features. And the least relevant feature for the model will be omitted. And then the process is repeated until the desired number of features is reached. In our case, we usually went for 10, 6, and 3 features and tried that out. And once we had the features, we trained the models. Here again, we tried different ones. Usually random forest worked the best, but we also tried neural networks and others. And just to go a little bit into detail here, for those of you who haven't heard of random forests before, a random forest is constructed by a multitude of decision trees, and a decision tree is basically a hierarchical structure where the different branches represent decision-making steps. And then in the end, we have several decision trees, every decision tree making a prediction, and the predictions are then averaged for the overall prediction. Now we can look into some results. What we did was we started off with 60 molecules in the beginning, and then we went for an active learning approach, meaning we did several training rounds, and in every round we added 5 molecules to our training data set. We always picked the 5 molecules that with the previous model had the highest standard deviation in prediction. And with highest standard deviation, I mean that I not only had one model, I had several models because I'm doing a cross-validation approach. Cross-validation means I divide my training data set into several subsets, and then I only train on one part of the data and taking one part aside for testing. And for every model, I use a different part of the set for testing. So I end up with slightly different models, and they all make a prediction, and then I can see, okay, how is the standard deviation in the prediction for the different molecules. And the ones with the highest standard deviation were then added to the training data set because they were adding the highest information, I would say, to the training. And we kept one blind test set aside for validation, and we could see that the error went down for the blind test set when adding new molecules to the training set. Here we can see the results for the inhibition efficiency and for the inhibition power as the target of the machine learning model. We could see the same trend, although overall the inhibition efficiency works a little bit better as a target. And now I also want to go into the platform and show you the landing page. So let's see. I hope that you can see the landing page now. As Marko showed already, when we go to the platform, we can see this. I already logged in, and then I can click here, and we can see the different apps. App 1 is the one for protective additives. And the first thing we see here are the key performance indicators. So the first one would be the inhibition efficiency. I already explained that. And then we also have toxicity and the price. For inhibition efficiency, we also have here the calculation, how we get that from the experiments. And then we get some information here. For example, we can click on this link and can see the training database. When we go back, we can now insert a molecule. So let's try this one. And so you could also put in the smiles if you have it for a molecule, but you can just search for the name. And now we have some links here. We can see the structure of the molecule. We have a link to REACH. We have GHS classifications, information on restrictions. We have information on toxic dosages, and we have chemical vendors. So if we want to look for the price, we can go through the list and pick one. And here we can then see the price for this molecule. So yeah, all the KPIs that I mentioned are here on this page. And for the inhibition efficiency, we can now use the machine learning model and predict it. So when I click on this button and refresh, then I can see the model is predicting 93% inhibition efficiency, which would be really good. Yes, and that's basically it from user case 1. And now the other user cases are coming. Thank you.
Thank you very much, Lisa. Very good. Next use case or application, it is inhibitor leaching performance from the coating matrix. And now Yelena will show us the modeling approaches for matrix microstructure, coating microstructure. Yelena, floor is yours. Please start your presentation.
Thank you, Natalia. Just a second. I hope you can see my screen. Hope you can hear me. Okay, so I'm Jelena Zaninovic. I'm a PhD student at Fraunhofer ITVM. I will be demonstrating App 2 today. It is the joint result of the work of a lot of people in the VIPCOAT consortium, but here we highlighted the people involved in developing of the app itself. So Katja Schladitz, Peter Klein, Tim Tassone, and Michael Gorehad. So the idea of App 2 is microstructure optimization. And what exactly do I mean by that? Well, one can influence the quality of the active protective coating by controlling the leaching behavior. The leaching behavior is strongly influenced by the microstructure, meaning the placement of the pigment particles and their shape and size distributions. Our aim was to observe real pigments, extract their geometric characteristics, and use them to build a stochastic model, hopefully matching the geometry as closely as possible. And then that stochastic model is used to create synthetic data in which we would perform diffusion simulations leading to leaching, which would enable the user to optimize the microstructure to get the leaching behavior that they're aiming for. For example, speeding up the leaching or slowing it down, whatever the user needs. For now, currently the app covers just the geometry generation part, but behind that is a lot of work and a lot of observations of many different pigment systems. So we performed measurements at the German synchrotron in Hamburg at DESI, and we collected nano and micro CT images of different kinds of coatings. We observed them dry, we observed them after getting in contact with water. We also performed some in situ observations. Overall, we collected more than 250 reconstructed 3D images, most of them quite large, most of them about 1,000 cube voxels. So at the beginning, we were trying to stay as close to the real coatings as possible, including different pigment types and titanium dioxide. But we decided to simplify them to just single pigments or 2 pigments at once, which improved the image quality greatly and enabled us to extract the characteristics that we need to construct our model. So we use the nano CT images to get these characteristics, and we use their phase contrast, absorption contrast, and holotomography images. In the paper linked at the bottom of the slide, you can find more details on how exactly we extracted these features, how we selected them, and how we constructed our stochastic model. So the model that we created originally is a more complex, sophisticated model, which models the pigments as polyhedra. However, for the app, we decided to go with a more simple model, which uses cuboids instead, which greatly speeds up the generation of the geometry, so the user can try out more things more quickly. For now, the user can choose geometric parameters, for example, the size of the observation window and the resolution, determining basically how big of a chunk of the coating you want to use for your leaching simulation. Then they can select the pigment volume concentration, or rather how densely the pigments are packed within that observation window. And then they can also influence the size and shape distribution. And for the shape, they can choose whether the shape deviates more closely to like elongated, rod-like, needle-like shapes, or are the particles more flat or platy. You can also choose to keep them cube-like if you want. So the user enters the parameters, and then the model generates the geometry. If the target parameters were not met, the model will warn the user. And then the user can take a look at these geometries, which will be rendered by the model, such as the ones here on the right. And if they're happy with them, they keep them, they use them in the leaching simulation, great. But if they're not happy, they just discard them and enter different parameters, try to get to the desired, better microstructure. Before I move on to showing you the app, I want to show you the variability of the results you can get. For example, here you have these different kinds of shapes. You have these platy shapes, cube-like shapes, and rods. And here you can see what the model will output for different pigment volume concentrations, from sparser concentrations to more densely packed coatings. That will be all for the background of the app. Unfortunately, due to some technical issues, I'm not going to be able to present the app in the OIP. However, I do want to show you how it works, so I will demonstrate the backbone of the app. Let me just switch to that. Okay. Hopefully you can see my screen. I will get the model running so I don't use up too much time. So here you can see the parameters that I mentioned before. So the first two determine how big of a chunk you want to be looking at. Then the next parameter determines the density of the pigments, how densely they're packed within the coating. And then these two parameters are going to determine the size distribution, and the last two will determine the shape distribution. Here I went for a very sparse, very sparsely packed coating with particles tending to be flatter. The model is pretty quick. Oh, it finished already. As you can see, the particles the shapes are not deviating too much, and when the shape is a bit off, it's mostly tending towards a flaky shape. I will run it again with the rod-like shapes just to show you what that looks like. I will change a couple of other parameters as well. So the model runs pretty quickly thanks to our choice of using cuboids over the polyhedra. But of course, your choice of parameters is going to affect the runtime. For example, if I wanted to generate a larger sample, if I increase the window size, of course, that's going to make the problem more complex. It's going to take longer to generate. If I pack the pigments very densely, of course, that's more challenging to perform, so it takes longer to execute. And of course, if I let the model have wild fluctuations in size or shape, that will affect the runtime as well. Now we just wait for it to finish. Hopefully we'll get to see an example of rod-like particles, and yeah, here it is. So now, as you can see, you can generate very diverse kinds of geometries using the model already. And that would be all from me. Now we can move on to app 3.
Thank you very much, Jelena. And I would like to inform the audience that we are working hard to integrate all these models in the platform. And I hope soon you can use this service directly from the platform. App 3 and App 4 integrated at OEP. And now I invite Nourhan to present App 3 inhibitor performance in a coating defect. And Nourhan, floor is yours. Please start your presentation.
Hello. Hi. Can you hear me?
Yes, we can hear you. Yeah, please start.
So hi everybody. I'm Nourhan from the VUB, and I'm here to introduce App 3. So App 3 allocation in the project is to try to give insight into the function of the active protective coating that will include the pigment particles or the inhibitor pigment particles chosen by App 1 and tested for leaching by App 2. So what are active protective coatings to begin with? The idea is that they provide passive and active protection to a metal surface. So in the case of the passive, that means that you have an isolated layer from the atmosphere, whether it's an electrolyte layer or just air, that would protect the alloy surface or the metal surface from corroding. Now, in the case of a defect occurring on the surface of the coating, you also have a solution for this, which is active protection. So in this case, you have particles, the inhibitor particles that are loaded in this coating layer that begin to travel from the coating to the defect to provide a protective layer on the surface. Now, so far the main used inhibitor has been chromate based, but now with its health hazard, the idea is to try to test other possibilities for their capabilities of metal protection. And to try to facilitate this testing and the choice, that's why we use finite element modeling. Now, what we're trying to do in the model is to study different domains within our geometry. So study what's happening in the coating. So how does this pigment, in this particular case, it's lithium carbonate, dissolve, and how it begins to diffuse or leach through the coating to the coating interface with the electrolyte. But also how what happens on the metal surface. In this case, it's aluminum alloy 2024. So beginning from the moment that it's exposed to the atmosphere, the corrosive effect that produces aluminum ions, followed by the protection effect of lithium ion by forming a layer. To do this, we use input data from two partners. The first partner is AkzoNobel. So in this data, we try to see how much lithium ion will be found in the electrolyte over time as it leaches from the coating. And the second is from our partners TU Delft, which relates the concentration, the initial concentration of lithium carbonate with the protection level on a aluminum alloy surface with the use of polarization data. Now, so for the both inputs, we do a bit of processing to use it in our model. So for our AkzoNobel data, we try to fit this leaching curve that is measured experimentally using a percolation model to obtain diffusion parameters, the parameters in blue here. With knowledge of the initial pigment concentration and the water content in the primer, the parameters in orange, and using these, we implement them in our model. The second set that we process are TU Delft data, which we try to fit using a Butler-Volmer equation. So we basically try to fit 4 parameters in the equation, as seen here, the blue circles on top. So the anodic and cathodic reaction rates and the transfer coefficients alpha and beta over different concentration of a mix between 0.1 sodium chloride and different concentration of lithium carbonate. Now, this is the background of our app, but what the user would see in our platform is basically this. A geometry which is composed of a defect depth within the metal, a primer covering the surface, and a top coat for isolating the primer from the electrolyte. And then a defect introduced to all of that with an electrolyte covering the entire surface. And for a user, the manipulation or the inputs are basically either through changing the geometry inputs or the environmental inputs or the solver inputs. We will go into details in the platform. And for outputs, the user can obtain the change in concentration in different species involved in the model. So whether the electrolyte species, as in sodium chloride or water ions, or dissolved air like oxygen and carbon dioxide, or corrosion products, so the different steps of aluminum oxidation, or for the inhibitor-related species, which is lithium carbonate and other species coming from reaction of lithium carbonate. This is over a domain average over time, or a maximum or a minimum, or through observing a 2D plot of the change in the electrolyte and the primer. So let's go to our platform. Okay, I just want to make sure that everybody can see my intro window in the platform. If I go to app 3, which is degradation in defect, you'll see at first a bit of a description of the geometry that we just described. So substrate, top coat, primer, and electrolyte. And then you will see the different inputs that can be manipulated. So first is the lithium carbonate concentration volume fraction, which is you can manipulate from 0.05 to 0.3. Then a simulation time, so how long do you want to see your model results? And mesh resolution that can vary between coarse and fine. It should be noted that as you increase the time of your simulation and the refinement of your mesh resolution, the model will take much longer to finish running. It can be up to a week or even weeks. So this is an important thing to choose at this point, so you don't wait for long while you want a not so accurate result or a not a longer simulation time. The second thing is the geometry parameters. So we can change the primer thickness, primer width, top coat thickness, defect width, and defect depth. The last thing is the thickness of your electrolyte layer and the concentration of the sodium chloride. Now, if I press build geometry, I will see my geometry that has been created on the right. And then if I go to the bottom and I say run process, it will tell me that the simulation has started successfully and I can get a notification when it's finished. Now, the notification will arrive here. And if I go to my user page for the user data catalog, and I check my app3 results, let's go to the very last ones. So this part, my colleague Marko has been a bit through it already, but I can just reiterate. So we have all the concentration of different species that we discussed in depth. So if I run this, I can see the change in concentration over time as the time step changes on top. If I scroll a bit more, I can also see the average concentration plotted. So in here, there is time. And at the bottom, I can choose what to plot on my x-axis. So if I plot against time, my concentration of hydrogen ion in the electrolyte, I can see that my hydrogen ion is being consumed over time, in average. And then if I go down, I close the table. You can also see something in the minimum and maximum concentration, a similar view. One thing that you can be done using this app is to try to compare different conditions, different initial conditions. So this is one study that's comparing a defect depth of 0 with one that is 100 micron, and I can see the changes in my aluminum hydroxide ion and lithium ion over time, as well in a 2D plot, as well as in a change of average value over time. Thank you for listening, and I hope this was good. Let me know if you have any questions, and I leave.
Thank you very much, Nourhan. Great. Yeah, very good job and very good results. Last application which we developed in the frame of the project. It is inhibitor performance under dynamic conditions. And currently, Mats will present the result. Here, Mats, please start it. The floor is yours.
Yes, thank you, Natalia, for the introduction. Let me find the relevant screen. Okay. In presenter mode. Yes. So within App 4, we try to make the transition from static water condition to more dynamic water conditions. So as we say, accelerated corrosion conditions. So this is an application that has been developed by VUB in collaboration with the people from Elsica. So in the platform now, there are two VDA accelerated corrosion tests integrated. And how do they work? I will try to explain you a bit. So the first step is we use based on the description of the VDA test that you can see on the left bottom, based on the description of the temperature, relative humidity profile, and the salt flux, we convert these contributions to a dynamic water layer thickness and a dynamic salinity using our dynamic electrolyte film corrosion model. As such, we can use this water layer thickness and salinity for the calculation of our species, of the concentration of our species. So we translate first the salinity and the water layer thickness into different flux contributions that are typically present in an accelerated corrosion test. So we have a rain flux. This is adding rain, and this is adding water and salt, so with a certain salinity to the solution. The second flux that we calculate out of the water layer thickness and the salinity is the condensation evaporation flux. So this is just condensation and evaporation of pure water. And the third flux is a runoff flux. So this is removing water with species, salt, but also the other species at the concentration they are at the moment. So this goes straight into our model, into our accelerated corrosion model, together with a memory curve, which is actually a leaching curve that is generated from AP3. So leaching curve saying the amount of moles that are present, that are leached from the coating over time, but that is translated to a so-called memory curve, and a memory curve is relating the instantaneous leaching flux dependent on how much species have already come out of the coating. So a little bit relating to what is left to what has already been released in terms of a flux. So the description of the accelerated corrosion test in terms of the three fluxes, rain, condensation, evaporation, and runoff flux, together with the memory curve coming from the leaching curve, goes into our accelerated corrosion model, which is called the ETIC model. It's an explicit time-integrated cyclic corrosion model. It's an Euler-based first-order numerical procedure, and as such, we are able to calculate over the volume of the water layer at all time instances, the pH, the corrosion products, but also the concentration of all species that are incorporated in the model. Now, there are two ways to do that. And the first is to start directly from AP3, since AP4 is an extension of AP3, and that is using the leaching curve that comes out of AP3 directly. And I will show you in the platform how we do this. So if you go to the platform, here we can select the AP4 interface, the accelerated corrosion test interface. Then you reach this page, which has initially some explanations about the integration of the different tests, also the literature behind it. And then you can choose here simulation type based on an AP3 result. So that is using a leaching curve that is coming from AP3. If you select that, you have to select which AP3 result that you have already run on the platform. You select the ratio of the anions and cationic inhibitor species. You don't have to change that. And you select which VDA test. So we have the VDA1 and the VDA2. You can see a little bit of information about the VDA test, also the temperature profile, the relative humidity profile that is used, and the description of the salinity that comes out of the VDA test. Then you have the option to choose for the same geometry as in the AP3 simulation, or you can choose a new geometry in case you want to work under different conditions. An alternative to providing the AP3 results is to just start from an experimental leaching curve. Imagine you have just done a leaching curve and you know what is the rate of leaching of your inhibitor. You can just provide a curve telling you how much inhibitor species as a function of time are released, and you can use that in an accelerated test, for example, to design your coating or to predict how long there will be active species present in your system under these dynamic conditions. So if you select the option for the provide experimental leaching curve, you need to say a little bit about that leaching curve. There are also instructions how to upload them. You can find them just on top. You have to say in that leaching test what were the dimensions of the coating, because we need to know, of course, how much, what is, let's say, the coating interface, the coating surface where the flux of the lithium goes through. Then the interface looks the same. with the selection of the test, and now you have to define your geometry because you chose your own leaching curve. You also have to define here the geometry you want to use. You choose the primer thickness, the top coat thickness. You choose the length of the primer. This is the depth of the primer, so how far the inhibitors are able to travel from in the coating to the interface with the defect, and the size of the defect, the width of the defect. You say build geometry, and then you can say set inputs, and you run the workflow. So then you have run an accelerated corrosion test, which takes approximately, at this moment, last time I checked, 20 minutes to calculate. So I already ran one a couple of hours before this presentation. And if you go to your own user page on the platform and you select your user data catalog, you have an overview of all the simulations you have done. So I have done a couple of App 3 simulations, App 4 simulations, but I also have uploaded here some leaching curves. So I have uploaded an experimental leaching curve with 15% PVC that I want to use in my accelerated corrosion test. If I here go to the accelerated corrosion testing results, there are a number of files appearing. The first one is the leaching test that I have been using for it. The last one is the memory curve that was generated from that leaching curve, so linking the instantaneous flux of lithium to the amount of lithium that has already been released. And then there are a couple of files related to the output, text files describing how the simulations went and in case of possible errors, and then the output file. If you press preview table, you can just select what you want to see. So as a function of time, we can, for example, see what for example, the amount of lithium that has been leached as a function of 168 hours, which is the duration of our leaching test. All other species that are defined in our system, the concentration of oxygen, water, the salt concentration, how that concentration evolves, we can now plot as a function of time. The last possibility is then that you also export this data as a CSV file, and then you can actually use this data yourself and do whatever you want with it. So that's it for the App 4 presentation. Thank you.
Thank you very much, Mats. Now we will start the second part of webinar. And here we will demonstrate the platform and will explain how to use the platform for innovation process, to start your innovation project and to involve different people with different expertise to give this collaborative effort to create something new. Marko Horvat will give the presentation and explanation of it, and after that Lisa Sahlmann will give you example of use case integration in the platform. Marko and Lisa, floor is yours. Please do it.
Okay, thank you very much. Me again. So for those who joined after the introductory session about the platform, my name is Marko. I'm joining you from London, and in this session I would like to continue the story. So what do you do actually once you are logged in and once you have a general idea of what is going on in the platform? I'll try to share my screen and hope that you can see the platform right now. Okay, so this is very kind of like the story. You are logged in, you have your user profile, you know where the parts of the different tools are, where the landing pages are, but how do you actually start using it, and how do you actually contribute to the community? And this starts with this innovation process that we integrated over at the bottom of that you can see at the bottom of the homepage. So the innovation process starts with sharing of your challenges, of something that you're currently working on. We call it here ideas. So by clicking on this plus button, you will be able to start sharing it. So clicking on it will redirect you to a form where you can enter the title, enter the description, the reason why are you submitting this idea. And here try to be as expressive as you can, because this is what other people will see as well. And where interested individuals who are using the platform will be able to join you on this quest of taking your idea and proceeding with it into something that is meaningful and that benefits the whole community. I will not go through it. It's just filling out the form and clicking the buttons. So let's not waste the time here. But once you have the idea, it will pop up just underneath it in this column of currently available ideas, where you can go and take a look also what other colleagues are doing. For example, I know Peter Mieris is working on some workflows for generating machine learning networks. This is quite a hot topic today, and VIPCOAT platform can help you in doing something with artificial intelligence, machine learning as well. I have created one example over here as a demonstration minus idea, and this is what I usually use for the demonstration purposes. And usually you can just click on it and you will be taken to a demonstration to this idea page. Now everything is in kind of a dummy mode. It's just demos and ideas, just showing you what this page could contain. So it has the title, it has the description and the reason why the submission was made. But here you can also start communicating with the people who are interested in this idea. You can start leaving comments. I don't know, a dummy comment. You can just post it, and this will then be visible to people who are over here. You can give impressions to this idea as well by liking it. It's kind of following the ideas that are present in all the social media platforms that everybody uses today. And from this idea, then you can start progressing. You can go from the idea to the project proposal, where you are starting to describe the steps of how this idea of your challenge will be carried out towards a project. So there is a currently available proposals from this particular idea. So there is a demonstration one. So it's again a dummy one, but let me just show you how this goes. If you did not have any proposals currently available from this particular idea that you started, you would be able to again click on the button over there which says proceed to a proposal or create a proposal. I forgot what is the exact name on the button, but you will figure it out. And another form will be presented to you, which you again will fill out with the title, description, and the reason of why this is being done. But here you will be able to share a bit more about your ideas and share a bit more about what you would like to do. For example, you will be able to say what is the required expertise of the future partnership that you are going to build. So for example, in this demonstration one, I am looking for people who know how to program. So I need somebody who knows how to do something in Python. I need somebody who knows how to do something in JavaScript, but I can add other skills here as well. This is kind of following the same idea to what was being done in your user profile. So you'll be able to come here and say, I don't know, a skill. I don't know. Let's do programming as well. And you will again be presented with the skills that come from the skills ontology, and then you will be able to add what particular skills would you like to see from the partnership that you are creating. Going to the partnership, you again click on the Go to Partnership button. If again, the same story, if you did not have the partnership created from this proposal, you will be able to initialize the partnership that is going to work with you on this quest towards the project. Going to the partnership, you have a interface where you can communicate with the platform and start searching for the team that is going to fulfill all of your required expertise that you mentioned in the proposal part. So I have here now all the skills satisfied, because this is already a longer running partnership which has a lot of users currently added inside. But if you are just starting, you will have an empty partnership over here. So how do you actually start building it? The simplest way is, the person who is already a member of the VIPCOAT community, and you go to find members by name. And here you can just start searching for it. For example, let's add, I don't know, let's take a look if there is somebody called Natalia in this in the VIPCOAT platform. If Natalia was not added to the platform, to this particular partnership, you would here have a button which says add Natalia to. Let's try something else. Let's see all the users that have A in their name. So Thomas is not currently a part of this partnership, but I could add Thomas because I know Thomas personally and I know that he is good at programming. So clicking on the add user, you will be presented by this kind of already familiar list of roles, because this is what Natalia mentioned in her presentation, the quadruple helix. And these 4 pillars are the main parts of the quadruple helix. So the platform will always encourage you to work in this quadruple helix framework, where the interaction between academia, industry, government, and finally society is what is the core of this collaboration. But you don't have to follow. You don't have to have a partnership which has all of the pillars of quadruple helix added. You can only have, I don't know, somebody from industry. When I click on add, what is going to happen is Thomas will be added to the list of pending users in this particular partnership. So if I go back to my members and scrolling all the way down, I can see now that the Thomas who has skills, whose job is a programmer, has a collaboration request sent to them. So at this point, Thomas has a new notification and a new collaboration request where he can come and say, I would like to join your partnership, or I would like to skip this time and not join your partnership. But this is quite simple and quite trivial. This is not something that is helpful for you if you're just starting and don't know anybody in the platform. So what we integrated on top of it is this functionality of finding members by skill. So what is happening here is you will get presented all of the skills that you mentioned in the project proposal, and you are able to click on a particular skill that you are interested in. Let's say JavaScript. When I click on JavaScript, now the platform is searching for a user which has skills in programming, specifically focusing on JavaScript. And what the platform will give me back is a list of users that fully or partially complete this skill. So here we are using the so-called semantic similarity computation, where you are able to compare different users based on the skills that they are using. And what we are using is the ESCO ontology. So if you go to Google and just write ESCO ontology, you will be presented by this European project, which is building the definition of skills and qualifications for general human resources purposes, but it's free, it's open, and anybody can use it. And this gives you a very good overview of what skills exists, what concepts in this skill ontology exists, and all the other things. And this is what we are using here. So the ontology is basically built as a graph, if you're not familiar with it. And what we are doing here, when we say that something is similar, for example, Python has 87% similarity to JavaScript. What we mean by that is we are assessing their Python's and JavaScript's relative position in this graph that is ontology of the skills. And in brief, if the skills are closer together in this graph of skills, or this ontology of skills, it will have higher similarity. If they are further away but still close to, but still related, they will have lower similarity. For example, scientific modeling and JavaScript, it's not so closely related as Python and JavaScript, so the similarity score is here 35%. But okay, not to bother you with these technical details, you just have to, the takeaway from here is that we have the functionality implemented which utilizes the semantic similarity, and the ontology is used as a background for where do these numbers come from. And also, if the JavaScript and JavaScript, if the user has the same skill as you are searching for, you will get the similarity of 100%. And this is pretty much it. But this is still kind of limited because different partnerships will have different different needs. For example, what if you need to carry out an interview before you want to proceed with this particular user and adding them to the platform? What if you have to have a bit of a back and forth? For example, if Thomas that I wanted to add to the platform would like to send me a counter proposal and say, oh, I will only work for you if you, I don't know, give me these particular tasks in your project, in your future project. This is where the workflows come into play. And we have here, this is a quite flexible functionality of the platform where you can build your own functionality into it. For example, a functionality of how do you add a user to the partnership. When it comes to workflows, they are always quite daunting to people because they look a bit technical. So for example, if I show you this particular workflow, it isn't, in my opinion, because it's quite straightforward, because you are just assembling like different blocks inside of this workflow of the functionality that you would like to execute. You see here that there are a couple of tasks in between the start event and the end event at the end of the workflow, and there are two different tasks that we are mostly considering over here. The one with the cogwheel in the top left corner is a service task. So what is going to happen here is the platform will execute a piece of code that is associated to this service task. And if there is a human icon, this sticker figure in the top left corner, this is a user task. And in this task, there will need to be some sort of an interaction between the user and this particular workflow. And what is happening in this particular workflow is, first, a user is going to have to give some information about the partnership. What information? This is specified underneath. So a user ID of the person that you would like to add to your partnership, partnership ID, so that we know what partnership are we talking about, the author ID, and that's it. Second is going to be another user task where a user is going to give a message. So this message is going to be sent to a user that is going to be either added or not added to the platform. And then the notification is sent to the user automatically because this is a service that the platform provides, and sends a message to the user. And then the user has a opportunity to either accept or not accept. In this simplistic workflow of adding users to the platform, there are two particular outcomes that can come out of this gate over here. You can treat this gate as a conditional or like an if statement if you know anything about programming. Basically, it evaluates a condition here, in particular this accepted condition over here, and it just does one of two different things. One, if the user declined, we just finish the workflow. And the second option over here is if the user accepted, then we add the user to the partnership, and then we finish the workflow. And let me just show you how you would create one such a workflow. You have this button over here, which is called Create New Workflow. Clicking on it will take you to the canvas where we utilize the BPMN standard. BPMN is a business processing and modeling notation, and it's a standard that basically defines the rules of how the workflows should be built. The first thing is you give it a name. I don't know, let's give it something that we know it's unique. It's a gibberish, but we will not save it anyway. And then you can start interacting with the canvas over here. So the first part is the start event. So every workflow needs to start somewhere. So we put the start event. And the last part that we will have here is the end event, is the button, icon, just 2 steps underneath the start event. And this is where our workflow will end. And then you can start interacting with it and adding workers, user tasks, and other things that we are providing over here. So clicking on this add worker will open a library of the currently available services that we provide. So for example, how do you send a notification to user? You don't need to quite know what is going around. You know that you have a pre-built template for it. So you just click on select. This will provide me two tasks that are needed for this to be executed. The one is give me inputs that you want to send to the user, and the second one is just the service that is being executed over here. And then finally, you just have to connect them further over here. And with this, you have successfully created a workflow. The workflow which will ask a user for a message, the user that we want to send this message to, and the particular partnership that we are talking about. Once you are ready to continue, you can store this workflow. And by storing it, Okay, now I put the one with the very gibberish name over here, but it will be presented for you just underneath the last available workflow definition that you have over here. You can still go back and forth with editing it. You can click on edit. It will bring you back to this canvas that you've seen before, and you are able to add another, I don't know, you can add another task or another service to it. Finally, there is another step you have to fulfill before this workflow is actually executable, is the request deployment. So what here is going to happen is a moderator or an admin of the platform will get a message that somebody would like to add a workflow, and then the moderator can accept or decline based on what is inside of this workflow. Let me show you how one of the deployed workflows looks like. For example, this that we started looking at before. Under the action toolbar, you will now have different options. So you are able to start it. And what will happen when you start it, workflow execution will be put at the bottom of it, where you are able to interact with it. So clicking on the action button, you will have this resume button, and here you are able to interact with it. So you are sending information back and forth. For example, here you will be able to say which user ID you would like to add. For example, I don't know, dummy user ID, and the dummy partnership, and the dummy author ID. And once you are ready, by clicking on the complete button over here, you're progressing in the workflow. So you're always able to click on logs to take a look at the logs. So you will be able to see here what is going on. And the logs here are quite straightforward because it's just 2 user tasks. And what we can see is that the workflow was started. You get the time stamp when the workflow was started. And you also get the information about when a particular task in the workflow has been executed. The second step, following the definition that we have seen on top over here, is to write a proposal to a user, right? And this is a particular user task that I don't have a permission to execute. That's okay. Then somebody else will have to come who has the permission to execute it and just fulfill here the field underneath. Okay, not to take too much time over here, I will go through the workflows once again when we are in the project pages, where I would like to go right now. So once you are ready with your team members and you are happy with the partnership that you have built, you are able to proceed to the project. I currently have a project which is running over here, and clicking on this button, go to project, will redirect me over there. So here you have a couple of options on the left navigation bar that you can utilize. So the workflows here is pretty much the same thing that we were looking at right now. So I have a list of workflow definitions over here that I am playing with and testing and developing new things. But I also have things like project data catalog. So this is kind of self-explanatory right now because we have already seen user data catalog a couple of times during these sessions. We have also seen a public one. This is the project. This is the data catalog that is available for this project and that this project has access to. So all the partners of the work of this particular project, your partnership, will have access to some results over here. So I don't know, results to the post-processing, some artificial intelligence models. So here, this is just the playground with the Elisa's machine learning model, where I was just looking into creating a workflow. Let me show you that one, which splits app 1. So in Elisa's example that she showed, she was running a workflow as well. But in that case, the artificial intelligence model was predefined. So it was by default set to the predefined model that Lisa created, and that was it. You were able to run this particular artificial intelligence model with a chemical that you would like to evaluate. But sometimes this is not enough, and sometimes you would need to have a opportunity to create your own artificial intelligence models. What if you have better data than Lisa has, or more data that Lisa has, and you would like to train it on this data? So here, the workflow is basically doing that. So first, some inputs for the training in this user task over here. Second, the service for the training, and then just some test run over here. What is interesting here is that this training app 1 service over here is storing the artificial intelligence model that is being created in the project data catalog. So if I go back to the project data catalog and just go to this app1 model, I'm able to, again, it's in the similar fashion like the colleagues showed you the results from their simulations. My result from my service can be an artificial intelligence model. And then I document it over here by providing some metadata on top of the files that are created. And I always have a reference that I can use. So for example, if I copy this ID to clipboard, I am able to now pass this to the next service in the line. For example, if I would like to run app1 with this artificial intelligence model, I just have to provide the service this reference over here. And how would this look like? Let me show you another example. For example, this over here, similar chemicals. So what we wanted to do here is extend the functionality of app1. And this is basically what these workflows allow you to do, to extend the functionalities of what currently exists in the platform. So if I show you the workflow, it's quite simple again. So first, what you are doing is you send a chemical that you would like to work with to the platform, and ask the platform, okay, could you find chemicals in the chemical database which have similar structures? And then the platform will send you the limit number of such chemicals back to you. So it will create a list of smiles and a list of chemical names as shown over here. The second, you will be able to choose what artificial intelligence model you would like to use. And finally, you will run a loop of app1 simulations on top of the list of similar chemicals that you retrieved back. So the idea is, if I know that a chemical is a good inhibitor, I can do this exercise with hope that I will find a better performing one which has a similar structure, which I'm maybe not familiar with, because from the Lisa's presentation you have seen how many chemicals are there. So it's not very convenient to run app1 simulation on individual chemicals. So how would I go about executing such workflow? Again, as previously defined for adding users, you click on the action drop-down menu, you click on start, you go down there, you take a look at what is currently the latest running workflow execution. I click on resume. I'm presented by this form where I'm able to add the name. So let's say Marko Horvat. If I did not misspell that, let's say I would like to 10 instances of this, and this is not a smiles. And when I click on complete, I will be able to go back to logs, and I will be able to take a look what is happening. So now my logs look a bit more like something is actually happening with this particular workflow. So I see that I have completed the task of providing inputs to this service. Second, I provided this data over here, so mercaptobenzodiazole with a limit of 10, and I get back a list of similar chemicals. So in the chemical name list, 2-mercaptobenzodiazole is similar, Zenite is similar, this salt is similar, then this chemical over here is similar, but I got these chemicals out pretty much for free by just executing the functionality of the platform. And finally, what I have to do here is give it a build target. Okay, let's take inhibition power. This is just something that is kind of related to this particular service. And model URL. Now I have to copy the reference that I've taken previously from the project data catalog, where I'm defining which artificial intelligence model would I like to use. And when I click complete, the platform will start executing the app1 on all the lists of the chemicals that I provided. And let's see if this is finished. Once it's finished, I will be able to go and take a look at my results, right? So now I provided a chemical mercaptobenzodiazole. I got back the smiles list and chemicals list. I chose which particular artificial intelligence models I would like to use in this exercise, and then finally I'm getting back the results for my list. So for 2-mercaptobenzodiazole, which has these smiles, I get back the inhibition efficiency of 84%. This is okay, not great. Then the Zenite is a bit lowering the inhibition efficiency, and then I can just go through the list and take a look, okay, what is my best performing example that I found over here. And then you could repeat this exercise. You could take your chemical which you found is the best performing, and you're able to just repeat this loop over it. And just to mention that this type of services are quite flexible, because you can build whatever you want. You can create your own service, you can register your service to the VIPCOAT platform, connect it to the workflow, and start building new things with the currently available resources that exist. So you will be able to create, for example, your own post-processing script of this particular similar chemicals workflow, where you are automatically taking out the best performing chemical, so that you don't have to scroll through this list of examples that have been run. And in such a way, you're able to contribute to the community and hopefully get some benefits out of the platform as well. And with this example, I would like to stop the presentation. Maybe I was a bit over time, and I apologize if I were.
Well, it's okay, Marko. Thanks a lot for details, discussion and introduction, and give more examples and details. Thanks a lot. Lisa, please start your part and provide example of a use case integration. And now we will demonstrate application 5. Please, Lisa, please start it.
Exactly, thank you. So I'm going to show you one of the workflows that Marko integrated into the platform. So first of all, I want to explain a little bit on the work we've done there. I hope you see my presentation now. This is about the design of AI-based workflow for coating performance prediction. So you've seen this slide before in the F3 presentation, so just a really short recap. So active protective coatings provide active and passive protection, as we've learned there. And we try to replace hexavalent chromium-rich coatings by, in this case, lithium-based coatings. And here, we have the active and passive protection, as I already mentioned, and through the defect, the primer is exposed to the environment, so pigment particles dissolve and travel to the metal surface to provide protection. That's the idea here. And as Nourhan already showed, the F3 model is focused on lithium carbonate, and it was tried to model the process occurring on the primer and on the metal surface. There were 2 types of experimental measurements, the leaching measurements and the potentiodynamic polarization measurements. But we have one problem here. The finite element model has quite a high model complexity, so the computation time for each study case can be really long. So our idea was to take some training data set from the FEM model and train a machine learning model to obtain the results if we want to run many scenarios faster. So we tried that. First step again was to build a database. In this case, we have 270 different cases in total, and it was generated by the F3 model. The inputs are the pigment volume concentration, defect depth, primer thickness, water layer thickness, and defect depth. And I listed the different values that we have in our training data set. And once we got that, we trained the model, and we got as the outputs the inhibitor concentration and the current density. The output was taken at 2 hours of simulation time, and it was extracted at the bottom of the bottom surface of the electrode. And the good thing about F5 now is that it significantly reduces the computation time, since it is trained on these cases from the data set, and now we can use it for predictions. to show you how well the model performs, I started off with the training and took only 10%, so 27 cases of the training data, trained the model, and then I stepwise increased the training data set to see if we actually have an improvement when we have more data. And as you can see, we have it for the first case, and we have a really bad model, but then with more simulation cases, the accuracy of our machine learning model gets really good. We trained a random forest and an XGBoost here. And we also, so the results are for 6-fold cross-validation. Cross-validation, I already explained that in my previous presentation. So basically having different models here for dividing the data set. And yeah, this is the results for the normalized root mean square error, same trend for the model with really few data points. We have a bad model, but then it increases. And now I want to go into this case here. So the 270 data points, here you can see an example for the prediction. So I always plotted the expected inhibitor concentration or current density on the x-axis and the predicted on the y-axis. We can see that for the inhibitor concentration, which is the first row, the prediction for training and test data set in blue and orange are really, really good. And for the current density, it's a little more scattered, but we can clearly see the trend and the prediction is still really good, so that we get an overall R-squared of 0.84. And the prediction, yeah, that's what I already mentioned. And here we also have the results for the XGBoost, really similar, really a little bit higher, 0.87, the R-squared. And now we can use the App5 model for coating optimization. How do we do that? We can use the model and predict the inhibitor concentration and current density for different pigment volume concentrations, as I did here. So I have taken the water width, defect depth, and water layer thickness and kept them constant. And I changed the primer thickness. That's the 3 different plots. And I changed the pigment volume concentration. That's on the x-axis. And then, yeah, we get the different current densities and inhibitor concentrations. So in this way, we can take a look how we want to design a coating, what would be an optimal coating for us, and use the App5 for that. Yeah, that's basically what I said. And now just a little insight into the model itself. So I plotted the feature importance. Basically, the pigment volume concentration has the highest importance here, probably because the leaching behavior from the primer changes significantly across the different pigment volume concentration values. And the water layer thickness is the second most important feature, probably because due to its influence, because it influences the replacement of depleted oxygen near the electrode. And yeah, that's it on the model itself. So we have this database from the FEM model. We used it for machine learning, and we get quite a good performance on that. And then we can use App5 for faster predictions. And now I also want to go into the platform and show you how that looks like with the workflow. So I hope you see the platform again. Starting on the landing page again, I can go to this project here and to workflows. And then workflows, all the workflows are listed that are available in this project, as Marko showed before. And here we have the App5 workflow. Now I can click on this and preview. We have this diagram here. And when we then go on start, we can scroll down and we can see here I started 5 workflow. And now I can put in some numbers. So it's all the different input parameters that I explained before. And now we can have a look how that works. Okay, I put in some numbers, click on complete. And now when I click here on the logs, I can see I started the workflow and now it received my inputs and it produced some results. When I click here now, I can see the results in detail for the inhibitor concentration, maximum and minimum, and for the current density. And also, since it's cross-validation implemented, so several models, we get a standard deviation. In this case, surprisingly, it's 0, but usually it's a little bit higher because the model is not perfect. Yeah, so this is basically how we can use the App5 in the platform. That would be it from my side on App5.
Thanks a lot, Lisa. And in general, it is full our planned program, scientific program. And currently, we will start this question and answer session. I would like to ask all VIPCOAT members open your camera. Because we have one kind request from Naomi to say some words about our collaborative work. But first of all, yeah, questions from our audience. Which questions, what is your thinking and your feedback to us, and maybe some requests to the team? No questions and no interest. So maybe it was only for our training to present our results one time more.
Can you maybe give a perspective view on what do you expect this platform to become for early career, but also for industry? Do you expect it to be more and more implemented? So now that the project stopped, what are the next steps, and what will be the future for this platform?
Thank you for this strategic question. What is our wish and what is our dream? Of course, we will be happy if platform will stay in life, and we will develop, or somebody else will develop this really powerful industrial, powerful environment for digitalization of materials to empower innovations. Currently, we have integrated these 5 examples and 5 applications. And we will keep the platform sometimes after the finalized of the platform in life. And after that, of course, we will be happy to find new opportunity to work on this topic. Thanks a lot to everybody, and thanks a lot for great questions. And I would like to repeat that we organizing this VIPCOAT focused session and roundtable and at Eurocore, and all corrosion experts are really welcome to go to our session, contribute for discussion, and maybe to look on the perspective of VIPCOAT platform, the same kind of multidisciplinary, multiculturalism, and really multi-fields, scientific fields projects. We are open for the collaboration and will be happy to find new partners and new field to investigate. Thank you.